Hello again everyone. This video is half Solidworks tutorial, half ANSYS tutorial. We'll then rotate it and put a load on it in ANSYS to simulate the bearing stress on the fin's connection to the body. The fin will be control roll of the rocket, which is one of the things our rocket will likely have to do this year. Start by opening up Solidworks and creating a new part. Once your new part window is open, actually I'm going to go ahead and maximize before continuing. Let's select the top plane and create a sketch. We'll sketch a horizontal line and then a vertical line. We'll click Escape to get out of drawing lines. And your lines will be horizontal and vertical if they have these symbols next to them. Let's dimension these two lines. The horizontal line will be 0.05 meters and the vertical line will be 0.1 meters. We're going to draw a couple more horizontal and vertical lines. Once again, hit Escape, go to Smart Dimension, and then we'll dimension these two lines as well. Let's dimension the horizontal line to 0.0625 meters, and the vertical line to 0.175 meters. Now notice it rounded these off. If you were looking at the sketch after we've done all this, you'd notice you have 0.18 instead of 0.175, and if you didn't know that you originally specified it as 0.175, you'd believe that was the true dimension. So you could click on that, you could double click on that to bring up the whole dimension and it'll show you this value, but let's take the guesswork out of it and change the precision to the amount that actually reflects the true dimension, which is 0.175. So you do that under the tolerance/precision section. You could do 1 decimal place, 2 decimal place, up to 8 decimal places. Yeah. So let's do 3 decimal places because that reflects the true dimension there. And notice this one was 0.06 instead of 0.0625. So we will edit this one to 4 decimal places. And there we go. Now that we have those lines drawn, all we need to do to complete this sketch is start at the origin. Whoops, that's an arc. Start at the origin, click on the top of the first vertical line, then we'll click at the top of the first vertical line again, and then we'll click at the top of the second vertical line. Click any green check marks that you need to get back to this screen. Now that our sketch is complete, we will extrude this fin by 0.01 meters, 10 millimeters. So you click Extruded Boss/Base. And since your sketch is 2 sections to it, you can click each section to extrude that section, and it'll recognize that you want to extrude the whole thing. Depth is already 0.01 meters, so we'll click the check mark, and now we have our extruded fin. Now, our rocket's fins shouldn't have sharp edges on the top like this, so we're going to smooth those out with a Camphor operation. To chamfer an edge, go to the arrow under Fillet, click it, and then select Camphor. Under the Camphor Parameters box, this is where we select all the edges that we want to chamfer. We're only going to do 2 at a time, because if we do 4 at a time, we'll get some weird geometry. I'm not exactly sure why, and there's probably a way to fix it, but I'm just because I don't feel like I want to investigate that right now. So we click the box. By default, it's already highlighted, and we're going to control click these two faces. Notice that the preview has a depth of 0.01 meters, which is far too much. The fin will just be super pointy by then. So we're going to change the depth to 0.00375 meters. We'll hit enter and then the check mark to generate it. So notice these are nice and, well, not rounded off, but they're edged to avoid those sharp edges. This is what you would get if you sanded the original fin. Okay, now let's do the chamfer for the other two edges. We'll control click these two edges this time. Notice even though the preview is only shown for one fin, both fins are selected. Always go by what's in this box, not what's on your screen. The depth is the same because Solidworks automatically carries it over. There's our chamfered fin. So if you had the regular fin, you would sand the edge that was formerly right there, and you get that flat face, and you sand that edge to get that flat face. Alternatively, you could sand to round it, which is a fillet. But anyway, we're done there, so we're going to make a hole for the connecting rod that will extend into the body of the rocket. To do that, we'll make an extruded cut on this face. We'll select a circle because we want a circular hole. A little side note, you may have noticed that there was a hole wizard up here. We don't want to do the hole wizard because that's better for things like screw. If we just want a plain old circular hole, we do an extruded cut. So you can place a circle anywhere because we want to dimension this next. So to dimension, go to Smart Dimension, click the center of the circle, then click the bottom of this face here. Place that dimension so that it's specifying the distance from the center of the circle to the bottom of the fin. We're going to specify that as 0.0625 meters. Notice it automatically changed for you. Once again, we have a 0.06 dimension there. We don't want that. We want 0.0625. We'll place that dimension. We'll Smart Dimension once again, but this time from the center of the circle to the edge of the fin extrusion. This one will be exactly 0.005. And now this circle is perfectly centered on this fin. Now notice this rounded up, and that's terribly misleading. So we're going to change that to 0.005. There's probably a way to change that default, but I'm going through it manually so that you don't forget. There's one more dimension that we want to do, or we want to place. The Smart Dimension, click the outer edge of the circle and specify the diameter, 0.0075. Notice that rounded up again. We're going to change that. Okay, now this thing is fully dimensioned. We know its distance from here, we know that it's centered by that dimension, and we know its diameter. Fun fact, that's the ANSYS symbol for diameter. Alright, now that we have that sketch, let's exit the sketch. And since we clicked Extruded Cut before sketching, it already knows to extrude the cut. We'll specify our depth as 0.04 meters instead of 0.01. Click the check mark, and we have our 0.04 depth hole. Now we're pretty much done with our fin in SolidWorks, so we're going to save it as two different file types. One for the assembly later on in video 5. You'll want to save that file, or I'll provide once we get to that point for video 5. The other file type will be for ANSYS. So we're going to go to the Save As button. The most convenient place for me right now is the desktop. So I'll save this as SolidWorks fin. The first file type is the SolidWorks part. That's .prt or .sldprt. I believe other CAD programs can read .prt, like Creo Parametric, for instance, which I also have installed on this computer. Alright, now that's saved, we'll save as again, but this time we will change the file type to a Parasol, which is .x_t. You can keep the same file name because it's a different file type, and we'll save that. Export all bodies. You always want to export all bodies. Now that we're done with that, we'll close SolidWorks and we'll launch Workbench. You'll want to make a static structural simulation, and we're going to jump right into engineering data before we do any geometry. I'll maximize this. Drag a static structural. Double click to edit engineering data here. We'll click to add fiberglass. Actually, I'm going to check that I'm still recording here. Alright, good. The last take I bumped F12 when I was pressing backspace, and that cut the video. But I didn't realize it, so I kept going throughout the ANSYS part of the video. And, well, I wasted a good 10 minutes there. Okay, so we have compressive yield strength and isotropic elasticity. We are doing the same thing that we did in the last video. Compressive yield strength is 750 megapascals. And for isotropic elasticity, we'll specify Young's modulus in megapascals as 30,000. And Poisson's ratio is 0.21. Hitting enter after each data entry. Alright, now fiberglass is fully defined, so we will exit engineering data. We'll double click to launch design modeler. The license warning for me, it won't for you. Or maybe not. If you've downloaded ANSYS onto your own computer, the license expires in about 30 days, November 30th. So you'll need to download a new license from the web and put it in your normal folder with the environment variable that points to that folder. But that's a different thing for a different time. Okay, to insert your Parasol, you go to File, click and click Import External Geometry File. There's this open dialog box. It says the type is PTC Creo Parametric, but that's just a feature on my computer. Because I've used PTC Creo to make Parasols before, it automatically assumes that it's from Creo, which is a terrible assumption, but let's double click that. Double check that it's a Parasol.x_t. Click the import feature and hit F5 to generate. Okay, the only thing that we'll be doing to this fin in geometry is rotating it by 20 degrees. So to do that, we'll first note that the sort of longitudinal axis of the fin here is aligned with the z-axis. If that's not the case, then you're kind of SOL. If you're watching this during a simulation video, well, you'll have to ask me what to do next. But this should be the default. It'll be aligned with the z-axis if you sketch it on the top plane in SolidWorks. which I hope you did. Okay, now to do the rotation, we'll need to create a axis about which to rotate. The easiest way to do that is to make a plane. So just create, go to new plane, and we'll insert a new plane in the outline. For the type, we want from face. For the base face, select the sort of bottom face of that hole we made earlier. Click apply. Then select the plane and hit generate. Notice a new coordinate system popped up here. But that coordinate system will only be in design model, or it will not carry over to setup. So if you have a coordinate system, or if you want to make a new coordinate system in setup, you'll have to do that in setup, not here. Alright, to do the rotation, go to create, body transformation, then rotate. Select the entire fin for the body, and for axis definition, go to selection, make sure that's checked, then click the axis selection box, select the plane. Notice this big red arrow is our axis. Click apply, and that's the plane normal vector that we just selected to rotate about. And that's exactly what we want, because in real life the fin will be rotating about this hole, because this hole will be where it's attached to the rocket, and that hole will have a rod through it that's connected to a motor that rotates the fin. In the angle box, let's do 20 degrees. Notice if you put a negative in there, negative 20 degrees will rotate it up. This is what we want it to look like. Let's generate that rotation. So now our fin is tilted 20 degrees in the negative y direction. So there's our z-axis, and there's a 20-degree angle right here. Alright, that's exactly what we want from geometry, so we're going to close that. And we're going to go to Model. Alright, now that we're in Model, we will mesh our material. We're going to insert a body sizing. So after you've inserted the sizing, select the body tool, click the geometry, and click apply. For element size, we will do 0.004 meters cubed. Hit enter. We will generate mesh. Update will also work for that. Check your node count. You should have around 24,000. Okay, next thing we will do is specify the material. It's nice to do this first, otherwise you'll probably forget. I forgot the last time I recorded it, or attempted to record this. So just to do that, go to material, then choose your material from there. Now the material's chosen and the mesh is done, let's insert a force. The geometry that we'll be applying this force to is the top face. We don't want to define it by a vector, we want to define it by its components. Now, if the rocket itself is pointed in the in the negative z direction here, and there's this 20-degree angle, we want our force to be in the negative z direction because the rocket will also be traveling in the z direction. So the force from the air will be hitting our face at a 20-degree angle here. That's why we've rotated it. And I hope you can see that some of that force will be deflected, or some of the air flowing over this will be deflected this way. which will cause the rocket to rotate about the z-axis in a clockwise fashion. Clockwise from the negative z-axis here. So we're going to define the z component of our force as 1,000 newtons. Make sure it's pointing down. Note that this is the positive z direction. Down is the positive z from the way we've defined our geometry. Alright, our force is fully inserted, so we will go to fixed support. The thing that will be holding our fin to this rocket is the connecting rod, and the point where this touches the connecting rod is that face. So we'll select that face and click apply. We will insert under solution, we will insert stress and strain. Actually, I did strain first, I'll do stress last. Everything should be fully defined, so let's solve this system. Should take about 10 seconds. Or less. There we go. First, take a look at stress. Notice that our force is on this face, although the centroid was probably about right here, so most of the force would happen there. Also, that might have been where I just clicked it. I'll have to figure that out later. But in reality, once we're experienced with fluid simulations, we will transfer the force from that fluid simulation onto this face. I just specified it arbitrarily because I got some numbers from a fluid simulation I ran earlier. So take a look at the stress. Analyze it using your experience from the past videos. Notice that it's most likely, or the fin is most likely to break on the inside surface of the hole and where the force was applied. If you switch to strain, you'll notice that most deformation is also around those areas. And something that you can do is switch the scale between undeformed and true scale to notice the actual deformation. It's not going to be a lot. So on this high-res monitor, I'm going to switch. Some of the pixels changed places by just a little bit. I'm not sure if you can see it on the video, but I can see it a little bit. I suggest you try this on your own. Your monitors probably aren't 4K in resolution, so you might have a hard time noticing it, but that will be the actual deformation. And if you want to get a feel for the general way this will deform, you can auto scale it up. Notice that the max strain is about 7 times 10 to the negative fourth, 7.6 times 10 to the negative fourth, and that's in units of meters over meter. It's about right there. So we'd expect the most deformation to occur there for this situation. Okay, that's pretty much it for the video. In the next video, we will be making 3 more of these fins. Don't worry, you don't need to make 3 new parts. We can just copy them. We'll make the body of the rocket, we'll make these connecting rods, and we'll connect everything using mates and rotate them accordingly and rerun this static structural with more forces and pressures, maybe even a temperature thing. I'm not sure yet because I haven't made that video.